All right, we are now onto the final video looking at how to do cross products. And we're going to do the hardest thing, which is two three-dimensional vectors. And we're going to look at this from a purely components and right-hand rules approach. Then I'm going to show you sort of a shortcut using matrix. And then I'm just going to write out an equation for you that you can memorize if you want to, but I'd really like you to understand some of where this is coming from. So let's get started with the two three-dimensional vectors. All right, these are the two vectors we're going to look at. This is A, 2 in the x, 3 in the y, 4 in the z. And B has some negative components to it. Negative 3 in the x direction, negative 5 in the y direction, but still positive 5 in the k direction. So what I'm going to do is I'm going to draw out what this would look like if we just look at A first. So 2 units in the x, followed by 3 units in the y, so a little bit bigger there, and then 4 units in the z direction, and that then gives me something that looks sort of like this as my resultant vector of those 3 components. Now, one way that we can kind of maybe help this make a little bit more sense is that this is the xy plane component, and then the resultant vector of A, or the total vector of A, is just above that, so it's just angled up from there. And a similar thing would occur with B, where I've got a horizontal projection that is like this, right? And it's just angled up from there so that it makes a 5 high sort of vector in the z direction. So that's kind of how I would draw them. What we can see here is that they are actually pretty close to perpendicular, would be my guess, although I don't know for sure what the angle is. So that makes the sine theta approach a little bit challenging when I'm trying to just find the size of it. But I also want to know what direction this is in. Now I can see pretty clearly that I've got A is kind of up and to the right, and B is sort of up and to the left. And so if I do my right-hand rule, that's going to suggest that the resultant vector is going to be sort of out of the page and maybe a little bit to the left. It's hard to say for sure, but that would be the direction that it would form. You know, if I have a parallelogram, that's going to look something like this. Okay, so not 100% right angle, but kind of right angle-y. So the next step is we're going to do every possible multiplication of these. Now, one thing that I'm going to do is I'm going to write this a little bit more generically to start with. And that's just to make this a little bit more generic so that we can look at this and see what this actually means. So now I need to multiply A and B. So I'm going to do this cross product, right? But this cross product means that I multiply AX times I hat by each of these components of B. And then I'll do the same thing for a YJ hat and a ZK hat. So let me just write out part of this. I'll get it started. So I have AX crossed with BX. And then I'm also going to have AX crossed with BY and AX crossed with BZ. So I'm going to draw these out, and we're going to look at what they mean and figure out what their areas are. All right, let's look at AX cross BX to start with. So I drew those out, and you can see that they're anti-parallel to each other. There's absolutely 0 area, and because there's 0 area, there's 0 directionality involved in this. That's just 0. If I look at AX cross BY, I get this image. A little bit more interesting. There's definitely an area here. So if I'm looking at this, it looks like, to me at least, that the area is facing in the Z direction. Now, is it positive Z or negative Z? For that, we're going to pull out a right-hand rule. All right, so I've thrown on my handy-dandy right-hand rule. Hand is coming out of the screen towards you, and then your fingers curl to the left, as you can see in the hand diagram, not when I do it, and thumb should be pointing down. So this is going to give us in the negative Z direction. that's the resultant area vector, is down like this. And it's just the size of AX times BY because this is a right angle. They're perpendicular to each other. So since this is a size of 2, this is a size of 5, this is negative 15 k hat. Negative because the right-hand rule says negative. Okay. Next up is AXBZ. All right, and if you do the right-hand rule here with your hand coming out and then curling your fingers up, your thumb will point off to the left as you see here. And that means that our resultant vector, because here's our area, so our area is facing sort of left to right, and we know now that it's pointing this way because that's the way that the thumb is pointing. So the size of this, I forget how big BZ is, it's 5. So this is, how did I get 15 for that one? My apologies. Again, scribble instead of erasing. Okay. So that's what we end up getting. We get negative 10 k hat for this pairing. We get negative 10 j hat for this pairing in terms of the numbers that we end up getting. Now, it's a little bit interesting here because in this case, we had a positive and a negative number, and we got a negative resultant vector. In the AX cross BZ case, we had 2 positive numbers, and yet we still somehow managed to get a negative number. What's going on? Well, I want to remind you of a particularly important sequence here, which is X to Y to Z to X to Y. Right? This is the general sequence in which you're supposed to go. This is the right way to go. So when we go from X to Y, we get a Z direction, K hat, and all that we have to essentially do is multiply the numbers, the coefficients, to their unit vectors. So since we had a 2 and a negative 5, we just multiplied them by each other to get negative 10 because we were going in the right direction. On the other hand, if we look at AX cross BZ, that's the wrong direction, right? That's heading back this way, X to Z. So we're going to get a Y direction thing, but because we're heading backwards, we're going to get the opposite of the product of the 2 components. Our 2 components were 2 and 5. That's 10, but we get the opposite of it because we're going in the wrong direction. Okay, what I'm going to do next is take a look at multiplying B, so not B, A and the Y by all the B components. And then we're going to do A and the Z by all the B components. And we're going to go through those a little bit faster. All right, so I've set up my AY times all the components of B. So we'll start with AY cross with BX. That, as with many of them, forms a right angle because they are along perpendicular axes. And so that gets me an area of a rectangle. This is 3. This is, negative 3. Yep, that's negative 3. And so I'm clearly going to get 9 as the size, but my thumb here, according to the right-hand rule, says that this is pointing up. So strangely enough, I get 9 k hat here. How does that work out? Well, let's just revisit our handy-dandy sequence. If I go from Y to X, that's backwards, I'm going to get the opposite of the product of those 2 components. Here I just get 0 because they're clearly parallel, there's no area. And then when I look over here, I have AY cross BZ. My right-hand rule tells me that the result is pointing in the positive X direction. And again, hopefully it makes sense if I go and look at my sequence, I'm going from Y to Z. Well, that's the right way to go. So since this is 3 and this is 5, that gets me positive 15 k hat. Not k hat. I hat, right? Because if I'm looking at my area here, that area vector is coming out this way, okay? So we're gonna take a look at AZ cross with everything. All right, so when we look at this, I've got my AZ cross BX, and according to the right-hand rule, that tells me that the area vector for this is going to be pointing this way, just from the right-hand rule. This was 4, this was 3, I think, in terms of its size. But I can see clearly that it's pointing in the negative y direction. So 4 and 3 gets me 12, but it's pointing in the negative j hat, right? And then when I look at this one, AZ cross BY, I see that my resultant vector for this area is coming out of the screen. And because this is 4 and that's 5, this should be 20 I hat. And then over here, you can see, again, there's no area, so I don't have to worry about that. Now, I just want to kind of go back and review one last time. I had a positive and a negative value, positive in the z, negative in the x. I ended up with a negative answer. Why is that? Well, because all I had to do was multiply the two numbers by each other. I can do that because I'm going in the right order. I'm going z, x to y. If I look at this one, I had a positive and a negative, and I somehow managed to get a positive result. I went in the wrong order, essentially. So when I look at this, I'm going from z to y to x. That's the opposite of the right way to go through a right-handed coordinate system. And as a result, I get the opposite of the answer that I would get by simply multiplying the two components by each other. So if I take 4 times negative 5, I get negative 20, but I'm going from z to y to x. That's the opposite of the right way, so I get 20 I hat. And then this one is 0 because they're parallel to each other. No area. So I'm just going to go back through, and what we can do is we could pair them up, right? So we see, for example, that I've got, that was not the color I was looking for. We've got a total of 35 I hat, and those two, we can see they're pointing in the same direction. We've got a total of, well, that's negative 10 j hat, and this one's negative 12 j hat. So negative 10, negative 12, negative 22 j hat. And then lastly is k. So I've got plus 9 here, and I've got minus 10 there. So that ends up being minus 1 k hat. So kind of as I had indicated, they were a little bit at right angles to each other. Now they were both pointing in the positive k direction. And so what we see is, because they were both pointing in the positive k direction, kind of similar amounts, similar size vectors, that we end up not having much of an area in the x direction, which kind of makes sense. If I got two vectors like this, they're forming an area that's essentially pointing in the xy plane somewhere, like horizontal, right? Not a vertical area. So hopefully this makes sense. Now, you don't want to do this every time you have to do a cross product, right? This is a little bit too time consuming. So what we're going to do now is we're going to try to utilize this the shape that we generated here sort of accidentally, not really accidentally, but sort of accidentally, to try to get a faster method of doing this. So I'm going to have AX, AY, AZ, BX, BY, BZ, and then I hat, J hat, K hat. So I've made it myself a little matrix, but I'm not done. I'm going to continue this on to both sides because rotation is sort of this infinite loop. So I'm going to go ahead and do AX, AY, BX, BY, I hat, J hat on this side. And over here, I'm going to have AY, AZ, BY, BZ, and then J, K. And that covers really any range of things that I might want to do. So here's how you can use the matrix to kind of do this, do what we just did above quickly and easily. The first thing that we can hopefully recognize is that going straight up and down doesn't do anything for us, right? Like if I multiply this column, I get 0. I get 0, I get 0 because the cross product of two parallel vectors, nothing. So then what I can do is I can make use of diagonals here. So if I go ax, by, I get positive k hat because I'm moving forward here. So one thing here is that I get ax, by, and that's times k hat. That's a k hat. But that's not the only combination that can get me a k. So I can also go this way. I can go from ay to bx, and I get a k hat as well, but I'm going backwards through my right-handed coordinate system. So I end up with ay bx k hat, and there's a negative sign there. So this is often just rewritten as ax by minus ay bx k hat. And then the next one that we'll look at is if I go AYBZ, I get an I hat. So AYBZ, that's I hat. And I went forward, so that's going to be positive. But I can achieve the same sort of thing by going backwards from Z, from AZ. So minus AZ BY I hat. And it's the opposite of whatever the product of those two components is because we're going in the opposite direction. And you can see that with the right-hand rule, hopefully. That ultimately all comes down to the right-hand rule. But this is a shorthand, sort of quick way of getting that result. If I rewrite this, I end up with AYBZ minus AZBY I hat. And then the last one to worry about is this one here. So I end up with AZBX J hat. And then I need to go this way. So I have minus AXBZ J hat. Minus because we're going the wrong way through our coordinate system. And that gives me AZBX minus AXBZ J hat. Now, this is just giving me what the area is in the K, what the area is in the I, what the area is in the J. What we typically do then is ignore this here. We simply add these up, right? So this plus this plus this. We can't actually add them to get just one numerical result, but we have an area that has components in the X, Y, and Z direction. So this is the equation that I promised you. So if you're looking for an equation, and you could write this in any order you want, this is the generic equation. You can see that if you multiply components together, you get 0 if they're the same components, but if they're one off forward, you get a positive value. If they're one off from each other backwards, you get a negative value. And the direction of the resultant vector is always perpendicular for a cross product to both of the vectors that go into making that cross product. So that's it. I've kind of gone through it all. Reminder that all that we're doing is we're doing lots of rectangles to get areas, and we're using the right-hand rule to tell us what direction things are going in. But we can potentially do it a little bit faster by representing things as a matrix, and we can go even faster by simply memorizing what this is. But this is hard to memorize, so if you ever forget, you can go back to the matrix, you can go back to the right-hand rule, and you can remember the sequence X, Y, Z, X, Y, gets you positive stuff, or it gets you just the result that you would get if you multiply the two components by each other. And if you go in the reverse order, so Z, Y, X, Z, Y, you get the opposite of what you would expect based on the values of the two components. And that's it. Hopefully this helps. Hopefully this makes some sense. And as always, if you have questions, let me know.